All right. Module one, big idea. We'll say, I was going to say functions and relations, but I guess it's relations and functions, I think they call it. Relations and functions. Sorry for the penmanship. Maybe I should type that. I don't know. We'll see. But anyway, for now, let's talk about this stuff. Relations and functions, and at least in our context here, when we think relations, let's think numbers and stuff for now, since it's a math setting here. Okay, so when we define a relation, really all we're talking about here is just a relationship, is the way that we would say it, in layman's terms, between two numbers or two numbery things. And so without getting super technical about it, we're used to dealing with mystery numbers. And so if we said like, okay, say we said X was some number, and then we had Y as some other mystery number, if we had just one number up there and it was just X and it's a mystery number, then, the game is always just, can I guess what number you're thinking of? Is it 5? Is it 7? And sometimes it's a particular number, and sometimes a number that changes a lot depending on whatever, Okay, but a relation would be, let's say we had a relation between two variables. I guess the idea would say this: all we'd have to do is define how these things are related to each other. We could say that they're equal to each other, and that would mean, well, whatever number I think X is, as soon as I figure out, say X was a 5 or something, well, then that would mean that I already know what Y is because if I put an equal sign between them, that means they're the same thing. So Y must also be a 5, But relations take all kinds of things, or all kinds of shapes. Sometimes it'll be like a different operator between them. Say we had something like X and Y. What I know about the two of them is if I add them up, then they add up to a particular thing. Say they added up to 5 instead of one of them being a 5. Maybe they add up to 5, What this does is it tells us just something about how these two different numbers relate to each other. It doesn't necessarily tell me what they are, because there's a lot of things that add up to 5. Like we could even keep track of that if we wanted to, and just kind of chart it out and be like, well, if X is this and Y is that. But if we say that X plus Y adds up to 5, there's a lot of things that add up to 5, as we know. It could be that X is 5 still. What if X were 5? And it's not to say that we figured out the mystery number. It's not to say X is 5. We're just saying, well, here's an example of what it could be, And there's a lot of things that add up to 5. It could be 1 and 4, as you guys know, or 2 and 3, 3 and 2. It could be the other way around. X could be a 3 and Y a 2, or you could go nuts with like 1.5 and 3.5 or something crazy. It could be like a 6 and a -1. The list goes on. I guess the idea with a relation then is us just saying, I've defined a relationship that tells me something about how these numbers work together, and it takes all kinds of faces. Now, a function, on the other hand, is a very particular kind of relation. And let's talk about that. A function, it's a very particular kind of relation. It is a relation. It's a particular relation, particular kind of relation. And here's how we could think of it, maybe, a relation. Pretend that all fit on there. Okay, it's a particular kind of relation. One in which we could think of I guess we could think of this as being like a machine where you would have inputs and outputs, a machine that chews up numbers and spits out other numbers. And so we could say this, I guess, and we'll get a better definition in a second, than just saying it's a, but I guess we could say like a machine that, and we'll keep talking about numbers here since we're in a math context here, but we'll say a machine that chews numbers, that, it eats numbers and then spits out other numbers. There's an input and output process, and I'm going to say predictably or reliably, and that'll be a big aspect of this. Let's talk about that for a second. I guess if we could say this, let's take homework machine for a second. There's an old Shel Silverstein poem called Homework Machine. Okay, homework machine. We'll just, don't worry about the poem. Let's talk about the machine itself. Take homework machine, which I probably should have capitalized, Take homework machine, for example. What if I said you were doing your homework and you found out, well, okay, I could just look up answers, somehow. Maybe you're using Mathway or something, or whatever. And you're like, okay, questions and answers, this is a math class, so the problems we'd have, questions or problems we'd have, they look like numbers, and the answers also look like numbers. So this works well for us, And so what if you took to the homework machine and you were like, well, okay, homework machine, oh, homework machine. What's the answer to, say, question number 3 or something, and you're asking, okay, question number 3, what's the answer, And then the machine says, whatever, and then it's all 7, is the answer. And then you're all, okay, well, what about, okay, let's try another one. Homework machine, what's the answer to number 8, And it's all 4, I guess, whatever. And then, none of this is a problem. You can keep on asking it questions. What's the answer to number 10? And it says, 23 or whatever. It doesn't matter. Everything's going fine until we get to this idea that we're like, what if you got to this place where you were like, I forgot to write down the answer. What was the answer to number 3 again? If this is a working machine, then what it better say the answer is, If you guys say, well, what was the question? Or question 3, what was the answer again? It better say 7. What if you were like, homework machine, oh, homework machine, what's the answer to number 3? And then it's like -5, I mean, something went wrong, at that point, I mean, the answer is not 7, and then the answer to the same question is -5. Like, it's not going to work that way. At that point, it's like, if you got 2 of the same input with different outputs, that means that I don't have a reliable or predictable output here. I should be able to say every time I put in a 3 into that machine, it should always give me a consistent, reliable output. If it says 7, it better keep saying 7. And if it doesn't, I can't trust anything about this machine. How do I know if anything is right? So if I have a function, I guess it's likened to a machine that works better than homework machine. A function would be something that you would have consistent, believable, reliable outputs from, And so maybe that's a good way to define function, more than just whatever we said about a particular kind of relation. Maybe we could say it's something like this. Here, we'll put a different color. And red, I guess. We'll say this, star. Nope, here we could say a function. Maybe a better definition for that could be something like, it's a relation with inputs and outputs. It's a relation with inputs and outputs. And I'm going to say, for outputs, we got to have reliable, consistent outputs. Consistent outputs. And this is, again, sort of a homegrown definition, but I think it gets the idea. Feel free to refer to a textbook or something for a more technical version of that definition, but this is the heart behind it all. Remember, we're talking intuition here. This is the idea behind it all. Okay, so let's talk about that. See if I can pull this color up here again. There we go. Okay. Let's talk about function then. Things that are functions and that are not functions, If we had a relation that is a function, here's a lot of them are. And so say we defined a function so that we have a relationship between x and y. And we're not just saying x equals y again or anything like that, or y equals x. But we said y equals 2 times as much as x, and then 5 more than that, That'd be a quick way to go about it. We could say, okay, is this going to be a reliable function, between the two of them, I can tell there's a relationship defined because we say, well, whatever the X number is, if I take 2 times as much and then add 5 on, that'll tell me what the Y number is, And so I could say there's definitely an X and Y relationship here. But is it cool enough that I could think of it as inputs and outputs reliably and consistently? If every time do I choose some X number as an input, will I consistently get a Y number as an output? And I think that'll work on this one as well as it does on many of them. So let's try, with this particular relation. What if we said, well, what if X were like, and again, this is not X is a particular number. We're just, spitballing here. Let's just say, what if X were like a 3 or something, We'd say, well, 2 times 3 then plus 5. Well, that'll tell me what the Y value is, then Y would be equal to whatever 2 times 3 is, and then plus 5 more. A lot of you guys, if you're running the numbers ahead, you might already have that answer for me, but here we go. We'll do it together. Let's not arrow it over there. Maybe we'll just do it here. And we'll say for the Y part, that'll be 2 times of the 3 and then plus 5. And then if you remember your order of operations, 2 times 3 is 6, and then 6 plus 5, we got 11 or whatever. And what we can tell is that this totally is a function, because now if I plug in a 3, again, this is me saying, homework machine, what's the answer to number 3? Every time I plug in a 3, you're going to do the same thing. It'll be 2 times 3, then it'll be plus 5. There's no way you're going to get anything but 11. It's going to keep on working. I'm getting consistent results out of this. If I plug in a 4, it'll be 2 times 4 plus 5, and that'll be whatever that is. 4, so 8 and 5 is like 13 or something, it's whatever. But every time I try that 3, I'm going to get the 11 as an output. A 3 in gets an 11 out every time, and a 4 in will always give me a 13 out, and we can tell by the nature of the operations here. And there's, always ways to tell. But we can tell this is always going to give me an 11 every time I do a 3, because I'm just doing the same old timesing and plussing thing, And so I guess we would say here, the way you would say this is that, oh, wow. Let's try and circle that again. This relation, this outputs, but not always is that the case. And so let's talk about that here. Sometimes you would get functions that work better than others, and so I'd like to contrast a couple of them. Check this out. What if we said Y equals X squared, plus 7 or something, right? Versus Y equals square root of X, that's a backwards of squaring, and then plus 3 or whatever. Let's not do 3 plus 5. Okay. Remember, the way we'll tell if something is a function or not, if these are both relations that define a relationship between an X number and a Y number, 2 varying numbers. But we'll be able to tell if we have a function or not if there is a consistent output thing going on. And so, well, okay, let's see. If I plug in some number for X and I say, well, okay, let's suppose my input number, if I put in a number X, then will I get a consistent output for my Y? And I guess specifically, I've been a little bit ambiguous here or vague. Specifically, we're defining Y as a function of X is the way we would say it, but whatever, we'll get into more of that as time goes by. Function or not is, I guess, what we're just going to say for now. Okay, in, out. If I define my X's to be input numbers and then the Y is just what I get out of it, then let's see if this works like a function would. Let's say if I tried a 3 again, well, 3 squared, and then plus 7 is how that would go. So let's see how our output would go. As we'd say, if 3 is the input, then my output would be put in 3 in there. It'd be 3 squared plus 7. And 3 squared, I don't be a 9. There's no 2 options there. It's just going to be 9. And then 9 plus 7 is always going to be whatever that is, 16. And so what we see here is, okay, I plugged in a 3. There's a way, it's just going to be 16, And so if I say homework machine, oh, homework machine, what's the answer to number 5? What's the answer to number 7? What's the answer to number whatever? And then I come back and I say, I forgot the answer to number 3. It's still going to give me a 16 because every time you ask it, it's going to say 3 squared, then plus 7, and it'll be 9 plus 7, and that's going to be 16 every time. Seems like that should always be the case, really. Like with any relation, as you're getting used to these, seems like that should always work. Like, why would it not work, you know? But there are different kinds of things that don't work. And so I wanted to talk to you guys about this. So yes, this relation is a function. We could say y is a function of x here, you know. But watch what happens with this. There's an issue that we run into with square roots, you know. And so if I think of x's as inputs and y numbers as outputs or something, okay, let's just take a note to the side here for a second before we deal with the function itself. Notice something with me. Remember, issue that we run into. Suppose now we're taking a square root of something. So let's choose a number that does that well. Maybe we'll do 9 since we were doing things with 3s anyway. Okay, square root of 9. Notice, if we took the square root of 9, that's like squaring, but backwards. We're finding a number so that when I square it, I get 9. And so in other words, whatever number I put here for being the square root of 9, it needs to be some number so that when I square it, it equals 9, you know? And so that's fine. I mean, 3 does that, right? And so whatever. But a lot of you guys, you might be thinking already, if you have some experience with this, or maybe you're just thinking it through, you'd be like, well, okay, so it could be 3, but also -3 could be the result of that too, you know, because really, and like this isn't totally fair, because really a radical is specifically talking about the positive square root, you know, that's just a secret of the trade. But we'll, for the sake of demonstration right now, instead of bringing up a weird function, we'll say, oh, okay, it could be a 3 or it could be a -3 is really what we're dealing with here, you know, because -3, if I square that, you guys might remember a -3 times a -3, that's a negative times a negative, you know, and that equals a +9 just the same. And so we run into problems here. And that's actually why we have defined this function to be this specifically positive square root over time. You know, I think that's why, is because we run into problems otherwise. But notice this issue is that if I take a square root of 9, it's either 3 or it's -3, you know. And there's plenty of other functions that run into similar issues, and then they become not functions, you know. And so, oh shoot, I just erased that wrong thing. Okay, there we go. Nope, it's still trying to be an eraser. There we go. Okay. So notice if we try and plug in numbers here, even if we choose nice numbers like a 9 or a 16 or a 25 or 36, you know, numbers that square root well, we run into problems, because I could say homework machine, oh, homework machine. What's the answer to question number 9 is my input. And it could say something like, well, that's the square root of 9 plus 5, you know. And that's fine, but we know that the square root of 9 could go 2 different ways. So that could be like, oh, it's either 3, or if I came back to it later on and I was like, what's the answer to number 9 again? Homework machine. And it's like, oh, that's the square root of 9 plus 5. And it might go with the -1 this time, you know? And so -3, you know, square root of 9, that could be 3 plus 5, or it could be -3 plus 5, and -3 plus 5 is not 8, it's like 2. And so at that point this is a problem where our homework machine is broken, and so you can't get reliable results out of it. If I ask it question number 9, it's going to give me some answer, and then if I ask it again, it might be give me a different answer, and I don't know what to believe. Do I believe any of these things, you know, or what is the case here, you know? There's no way of predicting which is the actual, well, like, what is your output going to be? What should it be, you know? And so in this case, we would say, well, the first one, yes, is a function, pretend that says yes, function. Here we would say, no, not a function. Y is not a function of x here. You might have that x is a function of y or something if you backwardize it somehow, but you don't have that y is a function of x, you know? We don't have this input and output working the way that we want. So we'll say not a function here, you know? And so this shows up in a lot of different ways. I wanted to just, while we're on the intuition thing, just got a little bit further but that is the basics of the idea behind what makes a function, and just a little bit more on all this stuff. Okay, so suppose we took the example of, there was a simple function we had before. We said, oh, this relation is a function, y equals 2x plus 5. We kept on plugging in a 3 and got out an 11. We plugged in a 4 and got out 13. Wanted to mention something about that. We'll take that function again, y equals 2x plus 5, because it's such a simple, nice one. Notice something about it, is we would say, well, okay, we can keep track of our inputs and outputs, x and y, viewing x as an input, some number you shove into a machine, and y is the number you get out of it, even if you know, there's a penmanship issue. And so we said, okay, I could plug in a 3, and then we had did 3 times 2 is 6 plus 5 is 11. Then we plugged in a 4, and then 2 times 4 was 8 plus 5 made 13. And and then we could keep on doing that, right? And then we could say, well, what if x were 5? What if I plugged in a 5? Then we'd have 2 times 5. Let's do that one. 2 times 5 plus 5. That's 10 plus 5 is 15. And a lot. I mean, this one is a very simple function, so you can start to see a pattern with the outputs. This is 11, 13, 15. If you keep on plugging in numbers in a row, you probably keep getting predictable results like you'd figure. It's a real simple function compared to some of the other weird ones out there, because I wanted to start with something simpler so we didn't get way perplexed, early on here. Let's try and avoid that as much as we can anyway. 2 times 7, I hope I'm not losing you guys. I know I'm talking fast. And so if we plugged in a 7, if we said, well, homework machine, what's the answer to number 7? Well, 2 times 7 plus 5 would be 14 plus 5, so 19 or something like that. I skipped an input. We didn't do 6, so it kind of broke up the pattern here. It's whatever. Anyway, here's what I wanted to bring up about it, is you can also, there's a visual way to represent this stuff. If we have a number line here that represents the x's and a number line that represents the y numbers that go with them, oftentimes it will use this visual representation. This is the Cartesian grid, or the Cartesian coordinate plane, or the rectangular coordinate system, or whatever else you want to call it. It's the XY plane, we call it, we put dots on the graph that represent the relationship between these x's and these y's. And so if we said we plugged in a 3 for x, we got an out and 11 for y, well, we can draw them. Say 1, 2, 3 was my x number, but before I put a dot there, I'm going to say, well, so we'll say, we got ourselves a way of keeping track of this stuff now. When I plugged in a 3 for an input, my output was 11. When I plugged in a 4 for an input, then my output was, if here's 11, then we'll be like 12, 13, somewhere around there. And then if I plugged in a 5, I got a 15. So if there's 13, then there's 14, 15, and etc. And so I forgot why I brought that up. Oh yeah. Anyway, this is another way for us to represent. It's kind of a visual representation, I guess we call it, a visual representation, or a graph, we call it, of all the different possibilities of the different numbers that could result, or I guess pairs of numbers that could result from this input and output relationship here, with all the numbers that get paired with other numbers in this relation. And so you've heard of graphing functions before, and graphing this and that. Well, this is one application of that. It's really all that graphing comes down to, because I know it can be intimidating. Really, the idea is just that. It's always just this. It's just saying, well, okay, what was my input number and what was the output that went with it? Can I put those together? I put in a 3, I got out an 11. So here's the 11 up that went with that 3 that I put in there. And then after a while, on some of them, you can see a pattern, This one's a linear function, we call it, because it makes a straight line pattern. It's whatever. Anyway, doesn't matter about all that. There's just, these are good ways we can visualize functions too. And then beyond that, the last thing I want to bring up is sometimes you'll see these things brought up where instead of saying y equals 2x plus 5, if we happen to notice that it's working as a function where this y thing seems to be getting consistent results as an output from the x's, then we can say, another way we'll say is, well, if I noticed it's a function, then we'll use function notation. Instead of putting like a y there, we sometimes will write this in a different way that reminds us that it's a machine, that has inputs and outputs. Instead of thinking just x and y, we'll think input and output. And the way we write that instead is, instead of saying like y equals this and that, oftentimes what we'll do is we'll say, oh, excuse me, here, instead of putting y equals 2x plus 5, if I noticed it's a function like that, then we'll say, we'll use what we call function notation. Function notation is just another way of writing this that gives a different perspective, that again emphasizes the input output nature of this relationship here. It is a relation, but since it's a function, we'll think of it as a function. And so we'll say, instead of y, we'll call it f of x. It's f parentheses x equals 2x plus 5. And it's weird that notation has that parentheses thing, because it looks like you're timesing by x, because oftentimes it will plug something in place of x and whatever's next to it like that too. It's timesing with the x, right? 2 times x. And so it could very well look like that is a parentheses timesing with the f, whatever that is, it's not really saying f times x here. This is our way of saying function of x, it's really us just saying the same thing as y and x here, except that instead of emphasizing this number and that number, now we're emphasizing the idea that one of them is definitely an input that gives an output. And so we're really just thinking of it as just one variable now, a variable of x with its outputs, And so do we do anything different? No, we could still say x and f of x, or x, and you could even secretly put a y there if you want, still. But our idea is that we're emphasizing the input output nature of it now. Thinking of any number you put for x as an input, and whatever you get out of that, well, we'll just call it the function output value, instead of thinking of it as x and y all the time. But it's still okay, secretly, it's still okay to call it a y over there. You'll very seldom ever run into an issue with that unless they have some other letter involved that they wouldn't talk about. And so it still works the same way. If I plug in a 3, it's still 2 times 3 plus 5, it'll still be an 11. It doesn't change anything. Only thing that's changing is a little perspective of us saying, I'm doing the same thing, but what we say here is, this is said, we say it out loud as function of, I put that, function of x. Or people say f of x is the way that we say it oftentimes, and then different functions will have different letters. Sometimes it's not an f, and we'll get into that more over time. Anyway, this is all I think I wanted to mention. Let me look at my notes here real quick. Bam, bam, bam. Wow, that's pretty good, I guess. Cool. Anyway, this is our basic intuition about whatever, about relations and functions. Don't tell anybody that I forgot. Anyway, thanks, guys.